Okay, so today I am going to discuss about the measurement of capacitance. Okay, so okay, so in case of measurement of capacitance, what we will do that like your measurement of inductance. So similarly, we are going to be use some bridge. Okay, bridge means it's look like the structure of that AC bridge is look like a piston bridge. So there are four arms, one detector. Okay, so one of the arm is unknown parameter containing unknown variables. Okay, that means we are going to find out the parameters of that unknown parameters of that unknown parameters of that arm, and rest of the arms are containing with the standard values of other electrical elements like resistance, capacitance. Okay, so measurement of capacitance also very important, but problem is that measurement of capacitance means if it is in variable in nature, so they are in more costly. Okay, so that's why some of the limitations are still there, as well as the capacitance having some insulating. There are two plates. Okay, in between two plates some dielectric mediums are there. Okay, so there is some that means there is some losses. Okay, so that called the dielectric losses. Okay, that maybe sometimes it's an issue. Okay, so as well as in our inductance, we are also considering that equivalent series resistance of the capacitor, that means ESR of the capacitance. Okay, that also been there. Okay, so what are the most important factors for measurement of capacitance? Okay, the main factors are there is that we are going to find out that unknown capacitance associated with losses. Okay, losses in terms of known external capacitance and resistance. Okay, so some losses are there in no terms of in external resistances as well as capacitance. So why that losses, that I am telling, that ESR component also be there, that may cause for some additional loss. That R is there, I square R loss will be there. Okay, as well as that delta component is also be there. Okay, so loss tangent, it is called tan delta. Sometimes we are also doing in high voltage engineering tan delta test of that insulator. Okay, so that delta also important issue. Then distortion dissipation factors. Okay, dissipation factor also associated with the delta, quality factors Q. Okay, that all kinds of parameters we are going to be measured. You know that for the inductance measurement of unknown inductance, we are also find out the Q. Okay, omega L by R. So XL by R. So in that case, the Q value will be 1 by omega XC into R. So sorry, the value will be like that omega c xc by r. Okay, so the value of x equal to 1 by omega c. Okay, so it will be coming that q equal to 1 by omega c r. Okay, for that capacitance. So ideal capacitor, for ideal capacitor, there will be a piece of dielectric material between two conducting plates, or it is also known as electrode. Okay, and the potential energy across the capacitor is thus dissipated in all real capacitor as heat loss inside is dielectric materials. Okay, there are chances for the heat loss dielectric materials. This loss is equivalently represent the series resistance, called the equivalent series resistance, that is called ESR, that I am telling about you. That ESR, just like your inductor, capacitor also having the ESR. Inductor also some series resistance. Okay, in a good capacitor ESR is very small, whether poor capacitor ESR is large. Okay, but one thing is that if you increase the value of capacitance, if sometimes we can observe that ESR value going to be less. Okay, if you see the data sheet of the electrolytic capacitor, you can understand that increasing of that capacitor value, that ESR value, sometimes it's going to be less. Okay, the lossy capacitor, the real lossy capacitor, can thus equivalently represent then the ideal lossless capacitor in series with that RC with the equivalent series resistance shown in the figure. So how they are associated, that means impurities, that R is impurity associated with normal capacitor. Okay, so in this picture we can understand clearly. Okay, so what are the important factors for performance of the capacitors that I have already discussed? The dissipation factor, quality factor or Q factor, loss tangent means tan delta. Not only that, permanent descriptions also be radio frequency applications. Okay, where radio frequency applications means where you need to vary the capacitor value. Okay, that frequency sometimes we need to change for, you know, that if you changing the channel like your FM, okay, frequency modulations, okay, FM station, if you want to reach some of the FM station, so what you will do, the frequency range, there is some frequency range, but individual FM having individual frequency. So what we are doing, we are changing, there is a pot, okay, potentiometer, so that pot we are rotating, okay. So changing of the pot means you are adjusting the frequency, and exactly when it will be coming 106.2, okay, there is some FM station 98.4, 106.4 to 94.3, okay, so these all are the FM station frequencies, okay, so you have to tune and reach that frequency, so you can say like that your FM is able to give that carrier frequency, and that carrier frequency, by that, through that carrier frequency you can access that FM channel radio station, okay. This is the basic concept of that RF applications, okay, where that variable capacitance is normally used, okay. The ESR and DF also particular important capacitor opening that power supplies the large dissipation factor may result large amount of power loss, okay, of the capacitor. The capacitor with high values of ESR will need to dissipate large amount of heat, okay. So your target should be like that, all the values should be in moderate in range. Okay, all the values should be in moderate in range. If it is not in moderate in range, so problem is that we are not getting that value accurately. Okay, so balancing will not be done proper manner. Okay, so I hope all of you able to understand. So what is that DF? The equations of the DF is equations of the DF is that I square R loss whole divided by I square XC loss. Okay, both the side current will be cancelled each other, so R by XC. So it is coming omega CR. Okay, Q value you already know that XC by R. So XC by R means what happened? Hmm. So XC by R means you know that if you replace that value, okay, so you will get that value. So tan delta, we are doing the tan delta test. Okay, so tan delta means again same thing, R by XC. Okay, this is just like reciprocal of Q. Okay, so here normally Q is XC by R, and here you see that tan delta is 1 by Q means R by XC. So it is coming omega CR. Okay, so Q equal to XC by R. Okay, you are replacing, so 1 by tan delta. So Q proportional to 1 by tan delta. Okay, so you can understand the delta value. Okay, tan delta equal to omega CR. Okay, directly you are getting that value. So it is resistive, it is capacitive voltage, and this one is your voltage. So it's impedance triangle, impedance, resistance, and minus JXC. Okay, 90-degree lagging with your R. So directly you are getting the impedance. Okay, as simple as it. I hope all of you able to understand. All of you able to understand? Hello, am I audible?
Yes, sir.
Yes, sir. Yes, sir.
Okay, if you have any kinds of doubt, you can ask me. Okay. Okay, so next thing is that resortive bridge for measurement of unknown capacitance. Okay, value of unknown capacitance we are getting by using resortive bridge. Okay, so we are using that value by using the values of standard capacitor. Okay, so normally that AB arm is used for unknown parameter. Okay, so C1 you need to find out that unknown capacitance C1. Okay, for branch AB, compared with the standard known capacitance standard values, that C2 is there, that C2 is there. Okay, then R4, R3, all are there and can be balanced by varying either of the non-inductive resistor R3 or R4. So we need to balance them. So you know that Z1 by Z2 equal to Z3 by Z4, as simple as it. Or sorry, I have Z2 by Z3 by Z4, or Z1 Z4 equal to Z2 Z3. Okay, so as simple as it. So you are replacing the value. What is the value of Z1? You know that the value of Z1 is only XC is there. Okay, so X equals to 1 by J omega C1. That is your Z1 Z1. Okay, it is your Z1. What is your Z1 by Z2? Sorry, Z1 by Z3. Okay, so what is your Z3? Z3 equal to R3. Okay, and this is your Z2. Okay, Z2 equal to what? 1 by omega C2. Okay, the or X C2. Okay, it is coming 1 by J omega C2, and it is your Z4. Okay, so Z1 Z4 equal to Z2 Z3. So you need to draw the phasor diagram. So one thing we know that sorry, for reference we are find out one thing. X-axis is there where just for the reference. Now we are getting to know that I1 some current is there. Okay, some current is there. We are taking some reference that I1 current. So what is our V1? V1 equal to J into, you know that what is your V1? V1 equal to minus I1, sorry, minus J I1. Okay, 1 by omega C1 or XC2, XC1. So minus J means lagging by behind with 90 degree with your current. So minus 20. So it is coming that it is your V1. So V1 point is there. Okay, you know that at balance condition what happened? V1 equal to V2 and V3 equal to V4 and V equal to V2. Sorry, V equal to V2 plus sorry, V3 plus V1 or V equal to V2 plus V4. That's the concept. Okay, so you know that V1 equal to V2, so that points also V1 equal to V2. V2 equal to how much? 1 by I2 by 1 by J omega C2. I2 by J omega C2, directly V2 is there. Okay, so directly V1 and V2 you are getting the point V1 V2. What is V3 and what is V3? V3 equal to multiplication R3 into I1, so it is your I1 into R3, so it is your V3 equal to V4. V4 is also be there. It is I2 R2, I2 R2. Okay, all are same. So this point is V2, V3, V4. This one is V1, V2. If you add them, so you will get the value of V. V is there as a vector. So what is the then you are balancing them. So that point is cut each other when omega j not equals to 0. Okay, so it is coming that C1 equals to how much value is there? C1 equals to that C2 R4 by R3. Okay, it is your unknown parameter that you are going to be find out. So directly you will get the value from here. Okay. The advantage of resortive bridge is simplicity. However, the advantage may be nullified, okay, by impurities creeping. Okay, impurities creeping in the measurement if capacitor is not free from dielectric loss. Thus, the method best suited for lossless air capacitor. So, the main boundings is that there is a chances for the impurities, normal ESR that I am telling about it. Okay, so if the ESR is there, so it is not working proper manner. Okay, so that's why we have to design for modified DSRT bridge. Okay, to make the capacitor more realistic. Okay, where the inherent dielectric losses you can find out. So you have to go for modified DSRT bridge. Okay. So in case of modified desortivage, we can see that one. So now your C is associated with some impurities R1 and R1 also been connected. Okay. And second case that another C2 was there in ideal cases C2 without having this ESR value. Now C2 is associated series with this resistance R2. Okay. So it is your VC1, it is VC2. R3 is there, R4 is also be there. Okay, so for the balance condition, it is your Z1, R1, capital R1 plus R1 plus 1 by J omega C1 whole divided by R3. So just like your previous equations, okay, set of equations. Okay, so now your cross multiplications, you are doing the cross multiplication, then your identity is there. So you are comparing that real component and then imaginary component. Okay, so from that imaginary component combination you will get the value of C1. Okay, and that comparison of the real components, you are also getting the value of R1. So as well as getting the value, so here you see the modified Resortive bridge. Okay, configuration and phasor diagram. Okay, so anti-clockwise rotation. Okay, as well as you are able to find out that D1. Okay, so tan delta 1 you are able to get. Just for a moment. Okay. Am I audible? Hello.
Yes, sir.
Yes, sir.
Okay. So here we can see the structure of that modified D-shorty bridge. Okay, we can also draw the phasor diagram. Okay, so first case, what was that one? So Z1 value is I1 R1 plus I1 capital R1. Okay, so it is your I1 R1 up to this portion, then capital I1 R1, that one. Okay, then you know that one I1 by omega c1. Okay, so if you add them, okay, if you add them you will get the value of v1. That value also same to your v2. V2 is what the value of v2 equal to I2 R2, this I2 R2, I2 R2, that I2 R2, I2 R2. Okay, then another thing also the I2 by j omega c2, really the v2. Okay, so this is your v1 and v2. Okay, same thing. Then what you want to get? You want to get that value of V3 and R V4. V3 equal to I1 R3. So I1 R3. So it will be in line of your I1. This is I1. So it is your V3. That point you are considering just like here V3. Okay. As well as it's similar to the V4. If you add them, so you'll get the value of V. So as simple as it V equal to V1 plus V3 or V2 plus V4. Okay, simple thing. Next, we are going for the design for the doing for the scaling bridge. Okay, so scaling bridge are the most popular the days of industries for getting the measurement of capacitance. Okay, dissipation factor and loss angles. So all the cases you can find out like your previous case. You can also find out delta. Okay, then DF. Okay, then Q value. Okay, so all sorry tan delta. Okay, so you can also find out these values. Okay, so similarly you can also do the same thing. So it this is your Z. Okay, this is your Z1. Okay, so you are rewriting over there Z1, Z1 by Z3, Z3 equal to R3. So it is your Z3. Then it is your Z2 and Z4. Z4 is the parallel of your R4 and C4. Okay, automatically you are able to get that value. That R1 you are able to find out unknown. This path all the time I am telling that is unknown. Balance condition B and C, these 2 points are the equipotential point. Okay, automatically you are able to get. Then then you are equating them. Okay, real part and imaginary part. Okay, equating them from the identity you are able to get the value. Okay, so it is your I1 first one reference is there, I1 is there. Okay, I1 is there means I1 equals to then what is V1, I1 R1, this is I1 R1 and I1 by j omega C1 this point. So if you add them, so you'll get the value of V1 equal to what? V1 equal to V2. So you are getting the value of V2 here. V1 and V2 equal to this point. Okay, V2 equal to only I2 what V2 equal to what? I2 by j omega C2. I2 by j omega C2. Okay, so it is your V2. So I2 by means minus that j, if you go numerator, it will be minus j. So V2 equal to minus j I2 means minus j means 90-degree lagging. Okay, so V2 is 90-degree lagging behind of your I2. Okay, so that means if you want to draw the I2, so that should be leading of 90-degree of your V2. So if this axis is if this point is for V2, so I2 will be where? I2 will be 90-degree leading. So it is 90-degree leading due to that J portion, J will go that side. So this is your I2. Okay, so you'll get the value of I2. Okay, so now, what is the value of V3? V3 equal to I1 R3. Similarly, it is your I1 R3, V3. This much is V3, I1 R3. Okay. So similarly, that V3 equal to V4, V4 equal to IR into R4. So definitely, what is your V3 equal to V4, IR into R4. So both are same. So I1 and IR will be the same axis. Okay, there is no difference, phase angle difference. So that is your IR. So what is your IC? IC current should be there, that you need to find out. If it is I2, I2 equal to what? I2 equal to IC plus I4. Okay, if it is sorry IR, IC plus IR. If it is IR, the I2. So here is the IC. IC is this one. So 90-degree leading. Okay, IC is 90-degree leading with this value. Okay, so it is your IC. Now you are adding them, so you'll get the value of I2. Okay, so this is also IC by equal to IC by omega C4. Okay, so you'll get that value. Now you can understand that V3 and V4, this is point. Okay, if you add them, so directly you will get the value of V over there. Okay, now you easily find out the other parameters also. Then measurement of frequency. We're going for measurement of frequency means bridge. Okay. So what is the function of frequency? All the cases, frequency is the function f for C as well as L. Okay, means omega C as well as omega L. Okay. So omega equal to 2 pi by f. So similar way you can also find out. Okay, for the bridge. Okay, so for the case bridge, you can also find out the frequency. Ions bridge is the primarily used for determination for unknown frequency. Okay, however, it can be used for various other application, including capacitance measurement, harmonic distortion analysis, and notch filter. Other also the audio and half frequency oscillator, half frequency oscillator. So where similarly that portion is unknown portion, so you are getting that I1 I2. Okay, that 2 points are equipotential points, so you are taking as reference I1. Okay, so I1 equal to what? I1 equal to I1 R1. So what is your V3? V3, you are considering this points V3 equal to I1 R3, V3 equal to V4. So V4 also I2 R3. So I1 and I2 will be the same axis. Okay, I1 and I2 will be the same axis. I1 equals to what? IR plus IC. IR equal to what? Sorry, V1 equal to what? IR into R1. Okay, so IR and I1 should be in the same axis. Sorry, IR equal to what? V1. V1 equal to what? V1 equal to V2 equal to I2 R2 plus 1 by j omega C2 into I2. Okay, so you can see that if it is I2 axis, so minus j omega C2 means this axis, this point. Okay, so I2 R2, so this portion is I2 R2. So if you add them, so you will get the value of V2. So this is your V2. Now V2 equal to V1. V1 equal to what? I1 into R1. I1 into R1. That means this axis and IR axis should be same. Okay, this axis and IR axis should be same. IR into R1. Okay. Now you are adding that what is I1? I1 equal to IR plus IC. IR plus IC. So directly it is coming I1. Okay. As simple as it. Okay, then your balance conditions means equipotential point, so you are getting that value. So from there here you are getting to find out C1. Okay, C1 you are able to find out C1 equal to, if you have the value of C1 you can find out XC1. XC1 equal to J. Okay, X1 equal to minus J 1 by omega C1. If you have the value of omega C1, so you can replace them directly. You are able to find out the frequency 2 pi f omega C1. Okay, directly you will get the value of frequency. Okay. So some numerical problems are there. Okay, based on the numerical problem, you can I'll share the slide so you can solve it the numerical problem to your home. Okay, if you have any kinds of confusion, you can ask me. And the time of exam, that type of problem will be there. Okay, so different numerical problems are there. Okay, to some other problems are there for also the assignments. Okay, so what are the problems? Just discussing over there. So for four bridges connected over there. AB is choke coil L1 series with R1. That one, that BC arm is that resistive, that only R3, and CD is capacitive C4, non-inductive resistance R4. Okay, non-inductive resistance R4. DA the non-inductive resistance R2. Okay, this is R2. So all the values are given. Okay, here you can see the values are given, frequency also given. Calculate the inductance of the choke coil. So as simple as it, you are condition getting the balance condition. So here you have to balance condition. You will realizing the circuits. Okay, so you know that condition Z1 Z4 equal to Z2 Z3. From there you are going to find out the unknown quantities. Okay, unknown values that you are able to find out L1, you are able to find out R1. Okay, that you are getting the two values. Okay, just for calculations, nothing else. Okay, so next problem is based on what, that four arms also be given. Four arms are given, A, B, B, C, C, D, D, A. The frequency given 500 hertz. Okay, then terminal also given, AC terminal. Okay, so other values like R2, R3, all those things are given. Okay, so now you also the other, you have to find out the other parameters, also dissipation factors. For valence condition you are configuring the Z value. Okay, finally you are able to get the value of C1. Okay, that unknown value, that this is your unknown quantity, so C1 you are getting, then R2 you can also get, R1 also you can get. Okay, so these numerical problems you can do it for that home assignment. Okay, so another thing also be there for the home assignment. Any doubt is there, so you can ask me, so we can rediscuss some of the questions. Is there any other, is there any doubt from your end? Is there any doubt from your end? Is there any doubt from your end?
No, sir.
Okay, so if there is no doubt, so our bridge chapter is completed. Okay, so if you have any kinds of doubt, you can note it down. Okay, in next class you can ask me, so we can rediscuss some of that points. Okay, so almost we are almost uh,